Welcome back. Oh, finally got my clapper after all this time. What do y'all think of these? I'm sorry I haven't been doing the shoes faithfully, but yeah, these are pretty nice.
Those are nice. They still have the thing in them, keeping the shape.
These are part of the 5 pair that I got the other day. So I haven't.
I never in my life have bought 5 pairs of shoes at the same time. I don't even know if I've ever bought 5 pairs of shoes in the same year.
Well, you know, I like shoes, and I'm not gonna, and I cannot lie. So, all right, we're gonna solve equations with logarithms and exponentials in them. So we got a lot to do. This might be a little bit of a long lesson, so we're gonna move on. When we're solving with logarithms with common base, we want to try to figure out if we can do it in shorter ways. Okay. So if we have the same base, then all we got to do is set those exponents equal to each other, okay? And with that power chart you might have in your hand or that you're familiar with, we can look and see if I can write 16 as a power of 2. And I can.
Yeah.
And think of this as...
So he said solve logarithms. In this case, he really meant solve exponential equations.
That's what I said. Yes, right. That's what I meant to say.
Yeah.
2 to the 4th is 16. 2 times 2 times 2 times 2 is 16. And I know that because I'm I got my little table power chart thing going on here. And if the bases are the same, then all I got to do is set the exponents equal to each other. And this is super easy. 3x minus 8 equals 4. And then I can do that. That's like gravy. So 3x equals 12. X equals 4. Lickety split.
So that means by that logic, I should be able to take 27 and write it as a power of, or nope, I should be able to write 9 as a power of 27.
Or 27 as a power of 9, or neither one of those work real nice for me. But I do know something about 9. I know 9 because I've had that one in my head a lot. I do know 9 is 3 squared.
Yeah, so we could replace 9 with 3 squared, right?
But that's going to be to the x plus 1. And then I'd have to look and see about 27. Well, 27 is another power of 3. It's 3 times 3 times 3. I do know that 9 times 3 is 27. So I'd have 3 to the 3 to the x. Oh, she's doing it. All right, now what do I do if I have a power to a power? Well, we talked about that in the power rule before. I'm going to have 3 to the 3x minus 3.
How about minus 9, Mr. Bobby?
Yeah, I did that on purpose. I promise you, I actually did do that one on purpose. That was not a mistake. Okay? I really did. I seriously did. You don't.
Sure you did.
Why is it minus 9? Do you think somebody out there might have thought it was 3x minus 3 besides me? Yeah. I gotta multiply the exponents, and the entire exponent is x minus 3. I really did do that on purpose. I promise you I did.
So you're using distributive property here.
Then this one's going to be what?
2x plus dose, as in dose.
Yeah, I have to take that 2 times the negative 1 as well. And now I just, I can take those exponents and solve, which is super easy.
So we could just subtract 2x from each side and add 9 to each side and get x equals 11. And guys, don't forget, you can always, when you're solving an equation, plug your answer back in, check it on your calculator, make sure they actually equal each other. Beautiful. Super easy.
Super easy. Okay. So let's see if we can't move on to a problem that puts a little more hair on my chest, because, that's what I want. All right. So, because you know what? It's good for you, Miss Young. It puts hair on your chest doing hard math problems. Okay. Anyway, and the other thing, when we defined logarithms, we talked about Miss Young did the little loop-to-do thingamajigger that she likes to do. If we
it's funny. I don't actually use this rule when I solve this type of problem, Mr. Robbie.
Oh, you don't?
I don't.
Okay.
I'm looking at this problem and I'm thinking to myself, okay, well, I want to write 17 as a power of 3. And I'm like, I can't do that. 17. Can't do that. Well, I mean, I could, but it's like some decimal that I don't know. And I could sit here and go 3 to the second, 3 to the 2.3, 3 to the 2.4 until I get 17. I could do that,
Yeah,
but I probably don't want to.
I don't really want to do that either.
No. So, but what I do know, because we talked about it before, is if I want to solve for an exponent, I could use a logarithm, right?
Right.
So there's two ways you could think about this. The way that Mr. Bobby's about to teach you, and then the way that I'm going to show you. So let's just do this two ways. Mr. Bobby, actually, you go first and talk about rewriting it.
Okay. Well, I was going to go with, I'm going from this guy back to this guy. So the base is 3. So I'm going to do log 3. And the exponent gets all by itself on the other side. And then that 17 goes in the logarithm. Now that log base 3 is 17, that's some number. That's like 2 something, right?
The one that I was just trying to come up with in my head?
Yeah, this, I can go like here and get that number, right? But that's just like, I could leave that be like square root of 7, okay? And then if I just divide by 2, I'm going to get x is equal to the log base 3 of 17, all divided by 2. I'm done. And I could plunk that in the calculator if I needed a decimal. I don't. Okay? So you do it.
So I hate having to try to think about like rewriting it from exponential form to log form, because I think it's easy to like make a careless mistake, putting something in the wrong place. But what I do know is like I can do anything I want to an equation as long as I do the same exact thing, right? So I could take the log of both sides, and I'll just use a common log so that I don't have to, I won't use a common log. Yeah, I'm going to use log base 3.
There's a reason why she's picking 3.
And so what would happen now is I'm going to do log base 3 of 17. I'm going to use a common log. Came from all those years of not having a calculator where you could change the base. Yeah. And so here's what's happening right now. 2x is coming forward. Log base 3 of 3 is how much? 1. So here is the inverse operation happening, right? Where I'm saying base 3 and log base 3 are inverses and they cancel each other out. I know y'all like that word. And now I'm left with 2x is equal to log base 3 of 17. And now I'm just where you were when you were rewriting, right? I can just divide by this 2, and it takes me to that same exact spot where you were. And then now, I just took the long way to do this. What in my head I would do is I would just say, I want to get rid of base 3. So I'm going to use log base 3. So let's do that. Yeah. Log base 7 on this side of 7 to the 3x plus 2 is equal to log base 7 of 58. And every single time the log base 7 and the base 7 in the exponential are gone, like they undo each other and leave you with the exponent.
And if you just like once you get log base 7 of 58, that's got all numbers in it. Just be like Paul and let it be, okay? Because it's just a decimal, or that would be some icky decimal. Again, I could get that decimal and work the problem in decimals, but then I got to deal with decimals. So I'm just going to let it go. And how do I solve for x? I'm going to have to get rid of that 2 by subtraction and then division by 3, right?
Yeah.
So I'm going to have log 7 of 58. Oh, thank you for putting the parentheses in for me.
This is actually the time when it becomes important to use the parentheses, because we're about to subtract 2. And we want to make it really clear that minus 2 is to the whole logarithm and not just to the 58.
If you write this, I have the choice of marking you wrong. I really do, because you haven't clearly communicated to me whether I could put the parentheses anywhere I want as the reader. Okay, I'm not trying to be a jerk here, but it's ambiguous because I could put the parentheses here like you wanted, but where else could I have put the parentheses?
On the outside of the 2.
I could have put the parentheses here, and now it's log of 56, which is entirely a different thing. Okay, so you really do. That's another reason why I tend to always put parentheses in. So even back here, we should probably have those parentheses added. It's not a bad habit to get into. Okay? Groovy?
Groovy, baby.
Baby. Oh my gosh. All right, Austin.
You think they know that reference?
Yeah, probably not. And so basically I was getting there anyway. I was going to do it. But that worked. The one that we did in the previous day was really nice because it worked. I only had one exponent. What? You don't like my
You're just waving around a dog booty.
A dog booty. Corgis have the cutest butts in the canine world. All right.
Oh my gosh.
All right. Oh, I hear your pug snorting again. So
yeah.
All right. So, but that works if you only have variables in one exponent, and it's great now. But if you have variables in 2 exponents, then
it still works.
It still works, but like I can't take log 4 of the left side and log 7 of the right.
That's
I have
true.
to do the same thing with what she was doing, where she's applying the log to both sides of the equation. It's the same logarithm. So I'm going to I got to choose, and I'm choosing either 4 or 7. Either way, one of them is going to go away, but the other is not. Okay? So I want to make the one that has the more complicated exponent. I would love to have the 2x plus 1 all by its lonesome, as opposed to having the x by its lonesome. Does that make sense?
I think it makes sense.
Okay, so if I do log 7, well, grab my pen. Ooh, there were some nice ones there. We're going to have chests after this problem. So if I do log 7 of 4 to the x equals, and can I just do 2x plus 1 on the other? I shouldn't probably yet. That would be
Guys, I'm going to reiterate what he's saying. If you're going to do log base 7 on the right side, you have to do log base 7 on the left side. If you're going to do log base 4 on the left side, you have to do log base 4 on the right side. You can't pick and choose your bases. Got to go with 1.
Yep.
So choose the one that has the more complicated exponent.
Because now I'll have 2x plus 1 all by its lonesome on this side. Okay? Now, I got that x in the exponent, but using that product property, I can throw it out front, right? So I'm going to have x times log 7 of 4. Ooh, yuck.
Ooh, yuck is right.
But what's log 7 of 4?
A decimal.
Hashtag. Wait, no, it's a number. It's some decimal. You ever see the Jimmy Fallon hashtag?
Mm-hmm.
All right. Yeah. So, but I know it's ugly, but it's like x times 2, or it's like x times, well, in this case, it's probably like x times 0.5 or something, some decimal. It's some icky decimal, but I don't want to work with that. But I have x's, I actually have a linear equation, so I can bring that 2x over. You want me to write the log in front?
I don't think it matters.
I don't think it matters either, but.
So what he's doing now is writing the log as the coefficient, which is a little weird to look at, but he's trying to really kind of hammer it into your heads that it's just a number. Log base 7 of 4 is just a number. So
I'm going to make a point of this right here. This guy and this guy, that's a common factor of x. I'm going to factor out a GCF of x, and then I'm going to have something else left over. Okay? So I'm going to have x times log 7 of 4, which I know some decimal. I just don't want to play with a decimal right now because I'm tired and it's been a long day. But I've got x times some icky decimal minus 2 equals 1. So how do I solve for x? I just
divide all that stuff that's multiplied.
Yeah, all that icky decimal stuff.
Yeah.
So I just have x equals 1 over the icky decimal.
Yeah.
And again, you really need those parentheses in this case.
Yeah. I'm going to kind of walk you through what just happened there so that we're really clear. The first thing we did was we took the log of base of both sides, and we chose the base that had the most difficult or most complicated exponent. What happened at that point is one of the bases went away. The other one had us bring down an exponent. After we brought down the exponent, it's taking me forever to write bring down. After we brought down the exponent, what happened at that point? Well, we needed to get x's together on one side. Everything with an x had to end up on one side of the equal signs. We had to get our x's together. Get it together.
That's a bad scene when the x's get together.
Yeah, that is a bad scene. After we put our x's on the same side of the equal sign, then we factored out that x. After we factored out that x, we were left with x times some ugly number. We don't really care what that ugly number was, but we just wanted to divide by it to get x all by itself. So this is what's going to happen when you're solving an exponential equation where you have exponents on both sides. You're always going to follow this method. Okay, so let's do that again, a little more complicated.
All right, so now we've got one with icky exponents on both sides.
Icky exponents.
And thank you for the dividing line. But yep. I'm going to choose, like, the ickier of the icky exponents is 3x plus 4. So I'm going to decide to do log 6 of both sides. And that would be 6 to the 3x plus 4. And that's nice because now I'm only going to have 3x plus 4 left, right? And then on the other side, I'm going to have log 6 of this 5 to the x plus 2.
Okay, so that was the log part.
Okay, so all I have left now is 3x plus 4.
And we have to do the bring down part.
All right, so I'm going to have x plus 2. Now watch yourself here. That times an icky decimal.
Yeah, so we actually, an extra step in this problem. Why do we have an extra step in this problem?
Because of that plus 2. I'm going to have to distribute log 6 of 5. Okay, so I'm going to have 3x plus 4. And I could go decimal. If you really like decimals and have a great love for decimals, you go on with your bad self. But me, not so much. Okay. So I'm going to have that log 6 of 5 times x plus 2 log 6 of 5.
Yeah. So if you have binomials and both exponents, there's going to be an additional step right here that is distribute.
Let me get here.
What are we doing now? Oh, we're putting our x's together. Get x's together.
Yeah, get our x's together because that's not a good thing.
Ooh, he's being.
Yeah, look at me being all sophisticated and fancy and stuff. Fancy.
So what just happened is he took log base 6 of 5 times x to this side. He took 4 to this side, but he also brought this 2 in and called it 25. You don't have to do that part. He's just being lazy. Actually, it's the same number of writings. He's just being complicated.
Yes, I'm being complicated.
And so he didn't show this step, but what happened here is he actually factored out an x from the left side, and he was left with 3 minus log base 6 of 5, which is what he divided by.
Yep. That's a lot of, I mean, that's not a trivial problem.
Not at all.
It's a, but you know, so, all right.
We're ready. We're not ready. We're not ready.
A quadratic exponential. What? We did this before where we had like x to the fourth and x squared because the exponents were double. So I want you to realize here that e to the x, back it up, slow roll that back.
We're going to have to solve log equations too.
You know what? I think we're going to make an executive decision here in a minute. So.
We are?
Yeah.
Okay.
If I have e to the x squared, that's e to the 2x, isn't it?
It is.
Okay. So what we're going to do, that middle e to the x is, if you square it, it's what's out front. So we're going to factor this in terms of e to the x. So if I wanted to, I could pretend like this is like some dummy I could call it x and then x squared. But e to the x times e to the x will give me e to the 2x. Okay? And now I'm just going to pretend like, I'm just going to say, you know what? You're like x and you're like x squared. Even though that was terrible. Okay? So
we're looking for factors of 3 that add to get -4.
So that would be minus 4 and minus 3, yeah.
3, yeah.
Minus 3 and minus 1. Super easy factoring problem, super difficult logarithm problem, or exponential problem, sorry.
So e to the x has to be 3.
Or e to the x has to equal 1. I was going to do that one. Why don't you solve e to the x equals 3 and I solve e to the x equal, well, how do, wait, we didn't do this with e's before.
That's okay. I'm just going to do log base 3e.
Oh, yeah, we're going to do log base e, and that's that natural log guy, right? Mine came out. Nice.
So can I leave my answer as log base e of 3? How do you feel about that, Mr. Bobby?
I would be happy with that. I mean, if you feel the compulsive need to grab your friendly neighborhood calculator and type that in, I'll do it just because somebody probably has that compulsive need. The answer that the calculator gave me is 1.0986. You know,
so the point here is
points for this though.
You could write this answer as log base e of 3 or natural log of 3 because that's the exact same thing.
Yeah.
Or you could even tell us that it's approximately I can't read that. It's all blurry.
0986.
Now, you do need to give us quite a few decimals if you're going to go to decimals.
Yeah, we need like 3 or 4 decimal places.
Yeah.
But you know what? I ain't giving you no bonus points for that.
Yeah.
Log base 3 is fine. So when we did when we're doing quadratics and polynomials before, if you got the square root of 7, just say square root of 7 and be done with it. We know you could type it in the calculator. That's not what we're after. Now, why does natural log of 1 equals 0? We talked about that before. If I thought about it as an exponential form, e to the 0 is 1 because any non-zero number to the 0 power is 1, right? So that makes sense. Okay? We good?
We're good.
All right.
So good.
Oh my goodness. And what I'm thinking is maybe we stop the video right now and split this into 2 videos since this is kind of long. And that's
I don't know how long we've been talking. We haven't even been talking 30 minutes yet. Let's get it done.
All right, you want to get it done? All right.
Let's get it done. The husband is still running. He was only doing 3 miles. So we're like,
let him off the hook.
Like 25 minutes.
So this is where we want to loop it.
Yeah, we're going to loop it now.
All right, so let me go back. So if we do the Miss Young log loop thing, you want to draw your little loop in while I write the conversion for you?
Already doing it.
So that would be 4 to the 3rd equals to 3x. And I can figure out 4 to the 3rd is 64. You do that problem. I'll do the one on the right side then.
And then it's simple, just divide by 3. Yeah. When you have a log equal to a number, you can always do this rewrite method, and it takes like 2 seconds. Yeah. So just kind of be keeping track in your notes of like, we're showing you lots of methods. So you want to make sure you're paying attention to what does the equation look like and what was the method that I'm now solving with. So this equation looks like log equal to number, and this method is rewrite to exponential form and solve.
And that's that one didn't have the base. That was the common log. So I remember I put the 10 in there for my mental state so that I would remember to do it. So, okay. Sorry for thinking you were done, but you know, you're not. So, all right. You're going to love some of these other ones. All right. So if, like Miss Young said, if you got a logarithm equals a number, you can go looping like crazy. But what if you don't have log equal number?
Well, and try to make log equal to number.
If you make log equal number, then you're good. But I don't. I have 3 times log. Well, I can get rid of the 3. And then I got log equals number. Okay? And that base is when it's natural log like that, in my mind, I know, oh, there's an E here, right? Oops. Maybe I should. There's that E there. So E to the 4 equals 2x. When I do that,
and guys, you can do e to the 4th in the calculator. It's some ugly decimal.
I don't know, you can let it be. Go. So
well, I don't know why you know, my brain likes to take them to decimals, but you don't absolutely have to go to a decimal. If you're, you know, tempted to go to a decimal, I think that's perfectly fine. But if not, no worries.
So
he's doing the same thing on this right-hand problem where he's isolating the logarithm, only this time the outside operation is -6, so we just added 6 to both sides. The fact that x plus 2 is inside that logarithm where you've got that plus sign is fine. It's no big deal.
Oh my goodness. I'm going to hate my life here if I try to put this in the calculator, aren't I?
Yeah, I don't even know if the calculator will tell you what 3 to the 30th power is, if we're being honest. I bet it gives you scientific notation.
Yeah.
So just leave it.
Yeah, I mean, that's what it is. And it would be, I could probably do it, but she's right. It'd be some icky monster number. But I can do 3 to the 30th minus 2, and I'm good to go.
Yeah. The awesome thing about getting into a college math class is like the way your answer is written, we don't really care about. We just want it to be right. So.
Agreed. All right, moving on. All right, now we got to bring those properties back. So what I would—
We can't get a log equal to a log on this one though, Mr. Bobby.
No, but if I have a log equals a log, then like if we had, when we had exponential, the bases are the same, we could drop the bases. If I have log equals log, I think I skipped, I might have could have done one of those. But,
That's okay, we'll do it right here. Look, log base b of m. If we had a log base, same thing, so let's say b equals n. I went too far over.
Yeah.
Equals n. What does that mean?
That m has to equal n.
That m has to equal n. So we actually really like it when we can write a log equal to a log, because that means we can drop the logs and just write what's inside equal to each other.
The arguments of the logarithms would have to be equivalent. So, but I don't have it, but I can get it there if I combine the logs on the left side. So, all right, and they're addition, so they're going to be combined through multiplication. So I'm going to get, oh, you're already starting it. So when I get log of x times x minus 5, you might be tempted, but I would recommend you do what Miss Young is doing here. literally write it out because I have seen way too many people botch this. What I'm going to get in that logarithm is actually log, oh my goodness, is log of x squared minus 5x. All right? And that's going to equal log 6.
Yeah. And now we have a log equal to a log. So at this point, we are no longer concerned about the fact that there are logs there at all, because what's inside has to be equal to what's inside. So we're going to just drop the logs off the equation. X squared minus 5x equals 6. Looks like a quadratic. I might try to factor it. So I would subtract the 6 over. Factors of -6 that add to get -5 sounds like -6 and +1, giving me two solutions, x equals 6 and x equals -1. Be careful, because when you're using log properties to solve log equations, you could end up with extraneous solutions.
And this goes back to the graph of the logarithm. When we did the graph of the logarithm, it only existed to the right side. It existed in the fourth and second quadrant, or the domain of the logarithm was for positive numbers. So I cannot take the logarithm of a negative number. So keep that in the back of your mind. If I put 6 in for x in the original equation, this one is good. This one makes me smile, right? But if I were to put -1 in there, this one would give me the logarithm of a negative number. And this is a false solution or an extraneous solution, like Ms. Young said earlier. So we had the extraneous solutions with square roots. We can get them with logarithms as well. Okay? And if you go through all this and you circle both answers and you're happy, you're still going to get partial credit, but I'm going to draw a frowny face on there. Probably there'll be a little like tear stain on your paper because Miss Young will cry.
Actually, not on your paper, because we won't be touching your paper.
That's true. We probably, yeah. Oh, I don't want to talk about such things. So if we can do the product property, we can do the quotient property. And again, if I had log equals log, I'm good, but I don't. But I have logarithm minus logarithm, which I could write as a fraction. So I could write this one as natural log of x squared minus 1 over x plus 1. So I want to try to reduce that expression. Well, what do I know about x squared minus 1? I'm going to do this over here because I think I'm going to run out of room. X squared is going to be x plus 1 over x minus 1, right?
Ooh, he's doing a little something extra right now. So he just factored the numerator, because it's the difference of squares, x squared minus 1 to x plus 1, x minus 1. He's doing that because he's noticing that x plus 1 is a factor of the numerator, which we talked about in a previous video. So he can actually rewrite this as natural log of x minus 1 is equal to natural log of 5, which makes it super easy because I've got a log equal to a log, so I can drop the logs off the problem, and
X cannot equal -1 though.
Yeah, so he's giving you the restriction that he caused when he did that removable restriction that we talked about previously.
And I'm really kind of anticipating if I get, I mean, I don't have to have that there for full credit, but if I work this problem and I get -1 for an answer of X, that's another extraneous solution, okay? So I'm going to get, let's see here, X minus 1. Ooh, this is an easy equation to solve. That I can solve, that's just 6. Is 6 a viable solution candidate? Well, 6 squared minus 1 is going to be positive. And 6 plus 1 is positive. I know it's 7, but it doesn't really matter. And it ain't -1, so I'm good to go.
Right. Now, I know what you're asking yourself, or I hope what you're asking yourself in your head is like, if I didn't notice that x plus 1 was a factor of x squared minus 1, and I just solved the equation x squared minus 1 over x plus 1 is equal to 5, would I get the right answer? And the answer is yes, you would get 6. You would get another solution too, though, and that solution wouldn't work. And so you would have to just make sure you go back and you check, and like he did at the end, to check your solutions. So if you did in factor, it's no big deal. Just this factoring will keep you from getting extraneous solutions.
And that may not always work, but if it does, it makes the process simpler. I'd much rather solve the equation x minus 1 equals 5 than that silliness that Miss Young has over there. So, all right, last example.
Phew!
This is a long lesson. All right, so now I got a property where I got the addition property, so that's like the multiplication thing, right? All right, grab your pen, silly goose. So can I just go straight to log at this point of x?
I don't know, they told them not to do it.
I'm not to, didn't I? But I'm going to do it anyway because it's the last example.
That's a really big plus
That's
sign.
a really big plus sign. I'm so tired. Are you tired? Are you tired, baby? All right. So now it's a log equal a number. It's not a log equals a log, but I know this is a 10, right?
Yeah, so I can rewrite. Log equal to a number tells me to rewrite.
So I have x squared minus plus 3x is equal to 10.
Yep, you did that in a different order than we've been doing it. So what he just did, guys, was 10 to the first is equal to x squared plus 3. He just switched the order. Yeah.
You might write it this way. That's fine. Same. Okay. Let's 10
and now it's just a quadratic, so let's subtract 10.
So x squared plus 3x minus 10.
So now we're looking for factors of -10 that add to get 3. Seems like a -5 and a +2 would do it. Seems like a +5 and a -2 would do it.
You were just going straight for the answers, weren't you?
No, I really just messed up.
I was trying to give you an out, but you wouldn't take it.
I'm perfectly happy with the fact that I'm not perfect.
I'm not. I'm perfect. My shoes are perfect.
And make sure we go back and we check our work here. So if I plug -5 into the first log, I get log of a negative number, which is sad. So we know that that guy is extraneous. So x cannot equal -5. And we plug a 2 in, we get 2 and 5 inside the log, and those are both fine.
Okay. So, okay. I think since I clicked ahead of B already, this is the
the end.
And that is the end of 5-5.
Bye, guys.
Bye.